In this video, we're just going to have a look at the first 10 out of the 20 bonding and structure multiple choice questions. So question 1, which of the following does not contain ionic bonding? Well, an H4, I need to think that's the ammonium ion. So although B contains no metals, that is an ionic bond still. And then if we look at D though, that does not contain any ions at all. It's a fully covalent compound. So the answer would be D. Number 2, when we're looking at lone pairs of electrons, I'm going to look at the group that the atom is in and then look at how many bonds it's making. Because if we look at A, boron is in group 3 and it's making 3 bonds, 1 to each hydrogen. So there'll be no lone pairs left because it's sharing all 3 of its electrons. With methane, carbon's in group 4, it's making 4 bonds. So I'm left with looking at C and D. Well, ammonium is made when ammonia, which does have a lone pair, reacts with hydrogen ion, which does not have any electrons at all, remember, and that's where we form our ammonium ion. That's a really common dot and cross diagram. Whereas H3O+ will be made when water, H2O, reacts with a hydrogen ion. And so the difference there is that ammonia started with 1 lone pair and then used it in a dative bond, whereas water started with 2 lone pairs and then used only 1 of them to form a dative bond with H+, and so therefore overall the H3O+ molecule will have a lone pair on it. So remember, ions can form by gaining or losing H+. Polarity. This is a shapes question for question 3 because all of these contain polar bonds, but we're looking for whether it has an overall dipole moment. I think I actually changed the wording of this question to be more specific. So carbon dioxide is linear, all the electrons used in bonding, no lone pairs. Sulfur trioxide also, all the electrons used in bonding, no lone pairs, which means everything spreads out to a trigonal planar. Same with boron trifluoride. So it's only ammonia where it's only using 3 of its electrons in lone pair in bonding, and therefore has a lone pair, which means that the shape is now pushing those hydrogens away, so we get an overall dipole. Okay. What's not present in ammonium chloride? So we talked about the ammonium ion and we said that ammonium is a positive ion, so there is definitely ionic bonding. We have NH4+ and Cl- attracted to each other. The ammonium contains covalent bonds within it because the nitrogen and the hydrogen are covalently bonded together within that. And of course, we've talked about ammonium forming through a dative bond, so that lone pair joining to H+. So there is also dative bonding. There's clearly no metallic. Metallic only works for elements. Okay, number 5 is just knowing your definition and knowing it is C. Why is it not D? So an ionic bond with always an any type of bond is an electrostatic attraction. There are examples where electron transfer can take place and yet no new ionic bonds are formed. So let's look at an example you probably studied at GCSE of displacement of metals. So magnesium solid will react with zinc sulfate solution and you will get zinc solid displaced and magnesium sulfate solution produced. If we were to write an ionic equation of that, the magnesium metal is reacting just with zinc ions and transferring electrons. So the magnesium is losing electrons and the zinc is gaining. If we look at the state symbols there, we're forming new metallic bonds because zinc is coming out as a solid, so there are going to be bonds between the zinc cations and the delocalized C. But my metal ions actually stay in solution. They're not joined to the sulfate ions. The sulfate ions are in solution surrounded by water molecules. There's no ionic bonding formed there, even though the transfer of electrons has happened. There are other cases where ionic bonds can form without electron transfer. So very simply, taking sodium chloride dissolved in water, if you boil away the water, you will get solid sodium chloride. So you've actually created ionic bonds there. The ions were separate from each other, and then they've come together as a solid. A precipitation reaction is another example where you make ionic bonds without having transferred any electrons because the ions were already there in solution. Before you mix them, they already had charges. So they are separate things. Ionic bonds are attractions between oppositely charged ions. Okay, linearity, we need to think about lone pairs again. And sulfur dioxide is not, because once it's shared 2 lots of bonds with oxygen, it's got 2 electrons left over. So if it's got 6 in its outer shell, oxygen needs to form a double because it always forms 2 bonds. That leaves it with 2 left behind once it's shared 4. So that is not linear. Water is definitely not linear. It's our classic non-linear molecule. And then OF2 would be exactly the same as water in terms of its shape. So it's beryllium chloride, and that is because beryllium is in group 2. Beryllium sort of behaves very much like a non-metal. And I realise I put a B there, sorry, but it would be linear, no lone pairs. Okay, phosphorus pentafluoride has a trigonal bipyramidal shape. So let's draw that shape, have a bit of practice. So I'm going to do 1 atom above and below my phosphorus, and then 1 is in the plane, and then 1 going backwards and 1 coming towards me. So there's 1 above and below, and then there are 3 all around the same axis. So it's basically like a trigonal planar shape with another 2 atoms above and below to stop it being planar, hence the pyramid parts, because it's 2 pyramids, one on top of the other. So 180 happens between the top and bottom. 90 happens between any of the bottom ones and the what we call the axial atoms, the ones around the middle. And if I was to take a bird's eye, so if I'm going to rotate that molecule around and look at it from the top and look at the 3 in the middle, you could see they're 120 apart. So it was 109. Sorry, that went for a bit fast. Okay, so information about ethane. We're given a structure and a bond length and a bond angle, and we're asked about ethene. It turns out, actually, if you know your bond angles, this was really easy. So the reason it was really easy is if we just draw it out, there are no lone pairs. There's very rarely any lone pairs in carbon unless it's got a charge, which you'll see in the longer answer questions. So if there are 3 sets of bonds, 1 double and 2 singles, then the bond angle is 120 degrees. And that's enough to answer the question. We could also look at the bond length. That is consistent because double bonds are shorter than single bonds. So when you need to put more electron density between the atoms, then the nuclei have to get closer together. So question 9, we're given a formula, potassium chromate 6, and asked for a formula of a different compound involving the same ion. So potassium we know is in group 1, forms a +1, which means that we can deduce that CrO4 has an overall charge of -2. Aluminium, from the periodic table we can tell is a +3 ion. And so basically we're going to need 2 lots of aluminium and 3 lots of my -2 chromate 6 ion, and that's going to give us Al2 CrO4 brackets 3. Number 10, which is the most polar? I am just looking for the biggest difference in electronegativity, and electronegativity decreases as you go down the group, so I need to pick the 2 elements that are furthest apart in the group. Fluorine's at the top of the group, iodine's at the bottom. So that's how I know it's the most polar. Don't be swayed into thinking that tells you anything about boiling points. boiling points here would be very much determined by the size of the atoms, and because as you go down the group you get a significant amount more electrons and therefore significantly stronger instantaneous induced dipoles.